Good afternoon and welcome to Advanced NMR Spectroscopy course. So today your sixth lecture and I'll continue with chemical sheet. So what we saw in the last lecture is the chemical sheet when hydrogen is attached to a heteroatom like oxygen. Okay, for example, we saw the chemical sheet values of hydroxyl group. Okay? And we have seen that it depends on the concentration, solvent, temperature, and extent of intra and intramolecular hydrogen bonding. This chemical shift of this OH, the hydrogen attached to OH also depends on the acidity of the compound. For example, the carboxylic acid. If you see the carboxylic acid, then next is stronger acid than phenol, then phenol is stronger than enol, and then enol is stronger than alcohol. And the chemical shift values are also follow very similarly. So, for example, the alcohols they problem. Sure. Software stuff. Okay, then again, I'll start fresh again. So today I'll continue the lecture on chemical shift. This is the 6th lecture in this series. Change नहीं हो रहा है. Okay, so in the last lecture, I discussed about the chemical shift of hydroxyl, the hydrogen attached to a hydroxyl group. And we found that it depends on the concentration, solvent, temperature, and extent of intra and intermolecular hydrogen bonding. Change नहीं हो रहा. Okay, now another class of compound where the hydroxyl group is there are the phenols, then enols, and if you see compare the acidity of these carboxylic acids, phenol, enol, and alcohol, the acidity increases from carboxylic acid. Carboxylic acid is stronger acid than phenol. Phenol is stronger than enol, and enol is stronger than alcohol. And the chemical shift also follow the same order, very close to that. For example, if you see the alcohols normally come around delta value of 1 to 4, depending on whether it is a hydrogen bonded intermolecular hydrogen bonded or 3-hydroxyl. And then you see the enol comes around 6 to 7 ppm. Then phenol around 4 to 7.5 ppm, and the carboxylic acid beyond 10 ppm. Okay, but if you see this this hydroxyl group, the phenolic, the enolic hydroxyl, are changing. Yes, sir. Changing. So if you consider, see, for example, if you see the 1,3-dicarbonyls, okay, you get the enol forms are always intramolecular hydrogen bonded. That's why the chemical shift value is quite downfield for such type of compounds. But for 2-hydroxycarbonyl compounds like orthohydroxybenzaldehyde or ketones and 2-hydroxy ketone or aldehyde, you see the OH appears very downfield, greater than 10 ppm, but it varies. It depends on the structure. So in summary, that when the hydrogen is attached to oxygen, you will see that they have a variable chemical shift ranging from 1 to 20, depending on the structure. And they are intermolecular or intermolecular hydrogen bonding, solvent, temperature, concentration. Now there is another type of heteroatom which is common in organic molecule is the nitrogen. So several nitrogen NH containing compounds are like amines. You see the chemical shift varies from 0.5 to 3.0 ppm. The imine NH, that also varies from 5 to 11 ppm. The anilines, the aromatic amine compounds, NH again varies from 3 to 5. Then another type of compounds are the carboxylic acid amide. The NH2 or NH chemical shift varies from 4 to 7. And you can see the quaternary ammonium salts like ammonium salts, it comes from it. The chemical shift is around 6 to 8.5 ppm. But if you see that, if you compare with oxygen, if you see the nitrogen, as nitrogen is less electronegative than oxygen, always you will see the NH signals tend to be less deshielded and appear at higher field than the OH proton. And as I have told earlier, that OH and NH signals are affected by hydrogen bonding, exchange, chemicals. Chemical shifts are also temperature, concentration, and solvent dependent. Now there is another issue which is not present in oxygen, but what you see in nitrogen containing compounds is the nitrogen. The 14 nitrogen is a quadruple nucleus because I value is 1, and because of this quadruple nucleus, it speeds up the spin lattice relaxation process or T1 process. So it affects the broadening of the signal. So due to this spin and coupling, combined effects make the signal appear very broad, and sometimes they are so broad that you may not be able to see sometimes they come into the baseline. For in this case, particular case, this is for the acetamide. If you see the acetamide, this NH2 proton, the CH3 proton comes around 2 ppm, whereas this NH2 comes around 5.5 ppm. But you can see it's quite broad actually. It started from 5.1 and almost up to 6.1. So one peak starting from 5.1 to 6.1 ppm covering. So it's a very broad peak, and that is due to the because of a quadruple nucleus, the nitrogen is a quadruple coupling is there, which speeds up the spin relaxation process, also the coupling. Now here I have summarized the proton chemical shifts, and already I have told you, and it is the summary, so it is a self-explanatory. You can see it, and whatever I have discussed are placed in this chart. Okay, so I will not go and discuss again. Now, another important thing in the proton NMR spectrum is that we have seen that the delta scale assigns the different protons in different chemical environments. Okay, but what we have seen that signal have different intensities. Okay, and you will see the area under the peak is proportional to the number of hydrogens that gives rise to that signal. Okay, sometimes the intensities, from the intensity you cannot tell how many protons are there. Rather, it is the area under the peak which tells about the number of hydrogens present in that signal. So here I have shown you one signal of one NMR spectrum of toluene, and if you see that there are two groups of proton, one is the methyl proton, which is coming somewhere here, and your aromatic proton, which are coming around 7 ppm. And if you see that there is a inbuilt electronic integrator in the machine which produces the steps curves. You can see it is a step. So it tells about these steps, the height of these steps tells about the or directly related to the area under these peaks. So you can see this is the step due to the aromatic protons, and this is the step due to the methyl protons, and you will see that the ratio will be again 3:5. Okay, sometimes these peak areas are, there is an inbuilt integrator in the machine, so that can give you the peak areas printed below the peaks. You can see this, and see you can make here it has been printed 5 because we have already told that there are 5 protons. Suppose if you make it 10, so then you will see that it is becoming 6.4. So you see again that it is now 3.27. It is not 3. So this problem we will discuss later on, because under the conditions where the NMR spectra is recorded, probably has not taken care of the T1 relaxation, because the T1 relaxation of the methyl protons are different than the T1 relaxation of the benzene protons. Okay, so if you do not consider, then you will see there will be a slight difference in the integration. Okay, so this integration is very useful actually. You can find out, or you can determine the constitution of a mixture or a percentage of impurity present in a sample. For example, I have shown the mass Ma of a compound A in a mixture can be determined if we add a known substance B. Okay, to a weighted sample of the mixture, and signals assigned to A and B are integrated. Okay, so you can see that this is the equation. The mass of A in the sample is given by Ma is equal to Mb, the mass of B, which we know how much of some Mb has taken, and then Nb is the number of protons, the signal which we are considering for integration, the number of protons present there. Na is the number of protons in your sample. Aa is the area which you got from either from the step curve or from the integrator which gives you the area, and Ma and Mb are the molecular weights of the compound A and B, and you can very easily find out. I'll give you one example here. Okay, so but as you know, the NMR is less sensitive method, so there is a good amount of error, about plus minus 3%. Okay, so here I have shown a sample. So to analyze the isotopic purity of tertiary butyl chloride, D9 tertiary butyl chloride. So what the sample is 200 milligram of both the CD3 whole thrice CCl and 200 milligram of dichloromethane is taken in a solvent CDCl3. And if you see, the NMR of this mixture, okay, so now one can find out what is the isotopic purity of this sample. So if you see the so what was the formula was M of A is equal to M of B into NB NB by NA, area of B by area of A, sorry, area of A by area of B, and to molecular weight of A by molecular weight of B. So now let us see molecular weight of A. Molecular weight of A is nothing but this, and that if you find out no, molecular weight of A, because deuterium we want to find out how much of tertiary butyl chloride is there, the protonated one. Okay, so for that, what is the molecular weight of that? That you will see, if you find, it will be 92.6 molecular weight. And if you see for MB is nothing but your dichloromethane, that is 84.9. Okay, so now you can find out M of A is equal to MB is, we have taken 200 milligram into NB is, now if you see dichloromethane is, there are two hydrogens, so we'll take 2 divided by how many are there? There are 9 hydrogens. Okay, there are 9 hydrogens here, so I'll put 9. Now area, if you see, therefore this is 0.15 divided by 2.0 into the molecular weight 92.6 by 84.9, and if you do all these things, you get a which is equal to 3.635 milligram. So in 200 milligram of CD3 whole thrice CCl, 3.6 milligram, let us say 6.635 milligram of CH3 whole thrice CCl is present. Okay, so what is the isotopic purity? So the percentage of D, if you do it, you will see that it is a 98.2% purity. Okay, so one can find out this way. So I have shown it is for a isotopic purity, but it can be applied for any other kind of impurity. Now we'll move to the chemical shift correlation for carbon-13. Now carbon-13 is like proton only, but only thing is, the difference is that now the natural abundance is 1.108%. Okay, and also if you see the I value of carbon-13 is also same like proton, but the gyromagnetic ratio is much less. Okay, is about 1/4 of the proton. So, and the precessional frequency of carbon is 10.7054 megahertz per Tesla. So there is the difference is that it's the major difference is in the natural abundance as well as the gyromagnetic ratio. So the receptivity of a nucleus for NMR at constant field B0 relative to proton, okay, is given by. So this is the relative receptivity, or you can say sensitivity, equal to the gyromagnetic ratio Q of that nucleus. For here it is carbon-13 divided by gyromagnetic ratio of the protons cube into Nx, means it is the natural abundance, okay, of that. For carbon it will be 1.108, whereas natural abundance of hydrogen is more than 99%. So you have to put all those numbers, and if you put all those things, you will see the relative receptivity of carbon-13 is 1:5700. That means whatever spectra you get for proton just by one scan, you require 5,700 scan to get the same signal to noise ratio. We'll come to this later on. So that's why the carbon-13 sensitivity is very poor. Okay, that is because the natural abundance of the carbon-13 is very less. But due to this natural abundance is less, there are two advantages. The first advantage is that you do not see the carbon-13 1H coupling in NMR. That is, otherwise your spectra could have been much more complex. And second thing is that homonuclear 13-13C coupling, spin coupling. We will see that later, because so far I have not told about anything about coupling, but we will see in future classes that what are the couplings. Okay, so see, there is no coupling between proton and carbon, and also you will not see in a carbon-13 NMR the coupling between carbon-13 and carbon-13, because of the probability of two adjacent carbons to be carbon-13 is extremely low because of the very poor natural abundance. That this is the thing you have to remember. Proton-proton you will see coupling, but carbon-13 couplings will not be seen in carbon-13 NMR spectrum. Now let us see for how to correlate the chemical shift of carbon-13. So so first of all, that we should know how the carbon-13 spectra are recorded. Mostly the carbon-13 spectra are recorded in a proton decoupled mode. Okay, so far again I have not told anything about the coupling or the decoupling. So we'll discuss this thing when we go for the coupling, and then we'll discuss decoupling. Okay, those things will come later on. But you remember this time being that all the carbon-13 spectra are recorded in a proton decoupled mode. So each carbon appears as a single line. Okay. The symmetry, now if you remember during the proton NMR, I discussed about the symmetry consideration. So whatever symmetry consideration I told you for the proton are applicable for carbon-13 also. So and then you will see the proton spectra I have just now discussed about the integration, but carbon-13 spectra are not integrated. The main reason is that the relative intensities are not necessarily proportional to the number of carbons give rise to the signal. What is the reason? Because the reason is that there is a large difference in relaxation time. That I was telling now, even in case of toluene, you see aromatic 5, whereas the methyl you are coming 3.2. But in carbon it is much more. And also when we are using a decoupled spectra, there are NOE enhancement in carbons where the protons are attached. Okay, we will discuss these things, nuclear overhauser effect. So you just timing, you remember that proton and unlike proton NMR, carbon-13 spectra are not integrated. The reasons are these two reasons, which we'll discuss in future classes. Another important point is the relative intensities of 4 tetrahedral carbon signal. If you see the CH4 intensity, you will see the CH4 is CH3 is greater than CH2, greater than CH, greater than quaternary carbon. This is due to the relaxation time. The T1, as I told you, and NOE enhancement. See, here you will see more NOE enhancement. Here you will also see more NOE enhancement. Here also you see, but there is no NOE because there is no protons attached. And not only that, there are the NOEs are coming from 3 protons. So the here relaxation also there, NOE is more. So that's why the order is there, the intensity order. Okay. And you will see the chemical shift range of carbon is much larger than proton. So you will see that a chemical shift range from minus 50 to 250 ppm or even more, sometimes depends on organometallic complexes, it is much more. Okay, now let us see like proton NMR, how what are the chemical shifts of sp3 hybridized carbons. So the simplest molecule is the proton. So the base value is used is the chemical shift value of methane. So and the chemical shift appears at minus 2.3 ppm with reference to TMS. TMS is considered as 0. So it is uphill than the TMS also. So if you see the chemical shift of number of alkanes and cycloalkanes to be used as the base value. So when we find out the chemical shift value of all these things, we will use these as a base value. Like for methyl or substituted methane, we will take this is the base value minus 2.3. For ethane, we will instead of minus 2.3, we will consider 5.7. For propane, there will be 2, this CH3 and this CH2. So you will get 2. The for C1 and C2, and you see here you will see 2. In case of pentane, you will see 3. Okay. Okay. Like that, hexane also you will see there are 3, because we will consider these as the base values. So we will consider these as a base value, this as a base value, these and these as a base value, these as a base value, and these like that. Similarly, for cyclic compounds, you see depending on which cyclic, whether it is cyclopropane, then we'll consider this. If it is cyclobutane, the values are cyclobutane, cyclopentane, and all these things have been given here. And you can see there is a slight difference, specifically the cyclopropane, and I have explained this while explaining the chemical shift of the hydrogens of a cyclopropane system due to magnetic anisotropic effect or ring current effect in cyclopropane. Okay, so now you see here the chemical shift. The substituent parameters for sp3 hybridized carbons. Okay, so what we will do, we will take the substituent parameters. Now you can see there are alpha, beta, and gamma. In one case it is terminal, another case it is internal. Okay, so let us see. So there is a slight difference when the substituent is in the terminal. You see these are the terminal. When the substituent is attached at the terminal, as you can see here. So the chemical shift, this is the halogen is attached to the terminal carbon. Here you see the halogen is attached to. For example, I have shown you the internal. So this is, you can see isopropyl chloride, the halogen is terminal, the chloride is in the internal, whereas in propyl chloride the chlorine is attached at the terminal. Okay, so and for cyclic system, you know, always cyclic system will be like, for example, if you draw a pentane, let us say, and you put, it will be always internal. Now let us see how to calculate this thing. Let us take the example of cyclopentanol. Okay. Okay, so if you go to the previous slide, you will see the base value for cyclopentane is 25.6. Okay, so what we will take? So we will take, this is your carbon 1, this is your carbon 2, and this is 3. So why we are taking only 3? Because there is a C2 axis and also sigma V. Okay, so you will see only there are 3 different types of carbon, 1, 2, and 3. So let us see what will be the value of delta 1 is equal to delta of base value cyclopentane plus delta OH alpha. Okay, so and if you do that, you will see that it is 25. You see those values 25.6, and when it is you see it is 63. So it will be No, for alcohol, it is 41. Okay. So it is 41. Okay. And you can add it. Similarly, delta 2, carbon 2, or will be same delta of cyclopentane plus delta, I will put OH at the beta position. Okay, so this is 2 position. Okay, so and if you put that value, you will see that it is 25.6 plus beta position. If you see the table, you will see this value is nothing but 8. So what will be the delta 3 value? Delta 3 value will be again 25.6 plus the gamma delta OH at gamma, and if you and if you do that, you will see 25.6 plus delta gamma value is minus, okay, minus 5, okay, and that value will come 20.6, okay, and if you go to this, you can see the gamma value. See, the gamma value is this is the beta value, okay. So those values only I have taken. I'll take another example. CH3, CHCl, then CH2, CH3. So you can put 2, 3, 4. So delta 1. All carbons are different in this particular case. Although there are 2 methyls, but they are different. Okay. So delta 1 will be. So delta 1 will be if you go to the, you have to go to the butane. So you have to go to the butane. Sorry, you have to go to the butane. You see the butane. So we'll take 13.4. Okay. So you go, that is the base value. So it will be delta butane plus delta Cl. You can see this is beta. Okay. So that becomes 13.4 as we have seen, plus beta position it is 10. This one, if you see at the beta position, it is 10. So it is becoming 23.4. Now we come to the delta 2. So delta 2 is now, we know that this value is delta 2. If you see from that, it will be delta 2 of butane. We have taken delta 1 of butane. This will be delta 2 of butane plus delta chlorine alpha. Same carbon it is attached. So delta butane is, if you see, that is 25.2 plus that is your it is now a internal chlorine, so that is 41. We know it's 41. No, chlorine is different. Chlorine is not 41. But OH was 41. So it will be equal to 25.2 plus delta chlorine alpha is equal to 25.2 plus delta is, that is 32. Internal halogen alpha. Okay. Now you see the delta 3 for the same. So delta 3 will be, again, it will be the 25.2 plus now delta chlorine beta, and we have seen that is nothing but 10. So it will be 25.2 plus 10. It is very easy. And what will be the delta 4? The carbon 4. Carbon 4 will be 13.4. That is the base value plus gamma, plus it will be delta chlorine gamma. Gamma is 13.4 plus that value, if you check in the table, it comes minus 4. Okay, so not necessary that a chlorine always will have a positive. Okay, it can have a positive, negative depending on position. And I have told you that this comes from the anisotropic effect of the bond. Okay, if you remember for proton, all those things are applicable here. Okay, so now let us see some heterocyclic structure, how you find out the chemical shift. So what we will do for heterocyclic structure, we will take the base value of the corresponding unsubstituted heterocycle. Okay, and then you can use the, so these are the values. You can see the furan, this is this is a nitrogen 5-member nitrogen heterocyclic, this is a sulfur thiophene tetrahydrothiophene. Okay, so this is the these are the 5-member, these are the 6-member, and you can see you can have only 2 carbons here because this is symmetry by the mirror C2 and sigma V. Here also C2 and sigma V. So these two carbons are equivalent. These two carbons are equivalent. So similarly for these. So we will take these values. These are the base values. Okay. And then we will see what are the effect of substituent. Okay. So I'll show you one example. Okay. For example, we'll take this. Okay. So this is so how will first let us see what should be the chemical state of this CH. So this CH3 is like this, a R group here, a R group here. So we'll consider this as a ethane as the base hydrocarbon. So we'll put this delta, we'll put this as a carbon 1, carbon 2, carbon 3, carbon 4. And you know, due to the C2 and sigma B, these carbons are also, these 3 and these 2 are equivalent, 4 and these are equivalent. So now let us see delta 1. So methyl group is delta 1 is equal to delta of ethane plus, you can see 2 times of delta of R at what position? They are at the beta position. Okay. So you will see the ethane is 13 point something, 13 point sorry, this is 5.7. 5.7 plus 2 into and you will see that it is 10. This value R group is 10. So you will see that it is coming around 25.7. So what about now carbon 2? Delta 2 will be piperidine C4, delta of piperidine C4 plus, so plus you will have a methyl group. Okay, so delta R alpha. Okay, so it is simple. So that comes around 25.9. If you check it, that is 25.9 plus 6. 6 is coming from this. Okay, so now similarly delta 3 now will be delta of piperidine C3, the way I have marked here, plus delta of R. Now R is in beta position. The methyl is in beta position. You see, with respect to this, now it is in the beta position. Okay, and then again 25, that value is different actually. So that you will see that comes at 27.8 plus 8. Okay, now delta 4 you can calculate. That will be your piperidine C2. So piperidine C, no, so sorry, this will be piperidine C4. This will be C4, C3, C2, and this is 1. So this will be piperidine delta piperidine C2 plus del delta of R at the gamma position. So with respect to this methyl is at the gamma position. So, and if you do that and you get the values, you check the table, it is 47.9 plus, that is actually minus. Okay. So del delta value depends on at what position, whether it is alpha, beta, and gamma. Okay. So this is another example. Okay. So this is the way one has to calculate. Now, like your proton, so vinyl carbons, if you see the carbons which are attached, which are involved in the double bond, they come around 100 to 165 ppm. Okay, and in that case, the ethylene was chosen as the base, and the chemical shift is chosen is 123.3 ppm. And now, if you see, if you consider this carbon, so this carbon you will have. You will have 2 alpha substituent and 2 A substituent. Similarly, if the chain increases, you will have beta, gamma, this side. So one side will call alpha, beta, gamma, and this side will call, if it is attached to the next double bonded carbon, we call them A, B, C. And accordingly, the substituent parameters are shown here. See, when this substituent is, let us say, R group, you will see if it is at the alpha position, it is 10.6. If it is in the beta position, it will be 7.2. In the gamma, it is minus. And see, when it is in the A position, it is minus 7.9. When it is in the B position, minus 1.8, and C position, minus 1.5. So depending on which group, not necessary. You can see that for all groups, depending on their position, the substituent effects or substituent values have been shown here. Okay. Now, when a group is in the B position or beta position, that means this alpha will be a carbon, alpha and A will be carbon substituent. When gamma and C and when the group is at the C or gamma position, both this alpha, beta, and A, B are carbon substituents. Okay. Now we see one example. Okay. So that will make the things very clear. Let us say the simple this one. So we'll take this as a 1, carbon 2, carbon 3, carbon 4, carbon 5. So this is your alpha. So let us first consider the this is your A, this is your B. Okay. Now consider the delta of carbon 2 is equal to. So we'll take the delta of ethylene, okay, plus del delta of R alpha plus del delta of R at R A plus del delta of R B, because you have both the carbons. So now we know that delta ethylene is 123.3. This is the base value, plus when it is at the alpha position, del delta R alpha, you see it is 10.6. If you see the table, you will see 10.6. Plus, you will see the RA, you will see it is minus 7.9. You will see that I'll show you, go back to the table, and for the B also, it is minus 1.8. Methyl means it is, we can consider this as a R group. You can see the R, the alpha is minus 7.9, B is minus 1.8, and even if there is a C, you will see a minus 1. And you see the alpha position here, the methyl, if you see the methyl is there, so that's why it is 10.6. So this is coming from the alpha, this is coming from the A, and this is coming from the B. So you can find out. Okay. Similarly, you can find out for this. In this case, this will be alpha. When you are considering the delta 3, So delta free will be delta C2H4 plus del delta R alpha plus del delta R beta plus del delta R A. Okay, and you will see the values will be different. 123.3 plus R alpha is 10.6 plus 7.2 plus minus 1.8. Okay. So you can finally find out. So this is the way one has to find out what should be the chemical septic values. Now the situation is little bit complex when you have a alkene where the substituent X is having a lone pair. So this lone pair can come into conjugation or resonance with the double bond, and it can seal this. You can see resonance means this will be a negative charge, so this carbon will be highly shielded, whereas this carbon will be highly deshielded. Or if the X is having a vacant, is not having a lone pair, but instead of that you are having a vacant orbital like carbonyl, nitro and cyano group, you will see the resonance in the other direction. You will see now this carbon is highly deshielded and this will be highly shielded. Okay, so that same thing only I have written in language, so you can read it. So once they are coming into resonance, so the alpha substituent can have a substantial effect on the chemical shift depending on whether they are electron donating or electron accepting. It is a common sense from the organic chemistry point of view. Okay. Now another classes of compounds are the organometallic complexes. Okay, where the alkenes actually they form complex with various transition metal. Okay, and they use their empty d orbitals to coordinate with the pi bond of the alkene. Okay, in that case you will see the vinyl carbons move upfield like protons. Now, if you remember yesterday I was telling the protons chemical shift were even minus 28 also. Okay, even the alkene protons were coming near 0 or even minus chemical shift. Okay, so similarly you will see the vinyl carbons also move uphill, and they can go even up to 7 ppm, from 123 ppm up to 7 ppm. Okay, so when the shielding is very high, you get 7, otherwise it is around 110. Okay, still it is highly shielded. The reason for this is that a shift is due to the shielding by the electropositive metal. Okay, so that is a diamagnetic shielding by the electropositive metal and the partial change in the hybridization. So when the metal bonds to the alkene, the hybridization changes from sp2 to sp3, and we have seen when you do that change, there is a significant change in the chemical shift, because we have seen all sp3 carbon comes within 40 ppm, whereas all sp2 carbon comes beyond 110 ppm. Okay, so these are the two reasons. Okay. Now aromatic carbon, this is another class of compounds which is very common, and here we consider the benzene carbon, okay, as the base value, which resonates at delta is equal to 128.5 ppm. Okay, and then depending on the substituent constants are shown here. You can see if the substituent is the alpha, means it is attached to the same carbon whose chemical shift you are trying to find out, this will be alpha. Next carbon is, if you are trying to find out the next carbon, then it becomes the ortho carbon. This is the meta carbon and this is the para carbon, and how the value changes. And you can see there is a positive, negative, positive, negative. So you will see in many cases this kind of changes happening. Okay. So you will see that in many groups their effect alternate back and forth from deshielding to shielding with no number of intervening bonds. For example, I've showed you that it is, you can see this is positive, this is negative, this is positive, this is negative. Okay, so this is happening due to the competing inductive and resonance effect. So if you, that depends on the substituent. If the substituent is having electron pair, so it can increase the electron density as ortho and para position. Similarly, if it is withdraws, you will see that there is a decrease in electron density as ortho and para with relative to meta. So I'll give you again one example for this, so that to make things little more clear, maybe one or two examples. Let us see one example. Okay, you consider this molecule. We'll put this as NH2, 4-nitroaniline. And now you see that first you see how many carbon signals you can expect. Okay, so if you see there is a C2 axis and a sigma V plane. Okay, so if in this case you will see that this carbon, this if we put 1, this will be 2, this will be 3, and this will be 4. So you will see that there will be, because this carbon, I'll mark this, and they have the same chemical shift. This will have the same chemical shift. So you have 4 different types of carbon. So this is your carbon 1. So how we'll find out the chemical shifts? So we'll take delta 1 is equal to delta of benzene plus delta of benzene plus delta delta NH2 of alpha plus delta NO2 at para position. So this is, you see, this is at the alpha, this group is alpha, and this is ortho, meta, and para. So if you put that value, it comes 128.5. If you see the table, this value comes as a 19.2, and this value comes 6.0. Okay, so now delta 2, how delta 2 will be? It will be delta benzene again plus delta NH2. Now NH2 is become ortho, okay, not alpha. It is now with respect to this is ortho position, plus delta NO2. Now NO2 is now in meta position. With respect to this carbon, it is in the meta position. So if you put those substitution value, it becomes 128.5 plus delta NH2 ortho position is minus 12.4. As I told you, so it back and forth, okay, plus 0.9. Okay, so delta 3 will be equal to, again, benzene 128.5 plus we'll use delta NH2 now meta plus delta NO2 now ortho, and you will see those values 128.5 plus delta NH2 meta is at 1.3 plus ortho is minus 5.3, and delta 4 is equal to, again, 128.5, and if you do that way, you will get this value. This is the substituent plus minus 9 point. You see how this, you find out how I have done. So this will be the value due to the alpha, okay, and you can calculate. So this, okay. So now, if you consider the heteroaromatic compounds, in that case, as you see, if you these compounds, you should take the base value from the parent hydrocarbon. And again, you must remember that for benzene, it was 128.5. But see, these values are substantially lower because, see, this is a 5-atom 6 pi electron system. So the electron density on each atom is much more compared to benzene. And if the electron density is more, the chemical shift value will be less. So in all cases, you will see. Okay, so this is a 6 electron. This is now this is a 6-atom 6 electron system. See that's why the values are very closer to benzene, but still there are differences. I will explain. Okay, and now this alpha carbon is highly deshielded because of the electronegativity of the oxygen. Similarly, for if you consider now this is nitrogen, and nitrogen is less electronegative than oxygen. That's why the delta value is slightly higher than this oxygen heterocycle. See, in case of pyridine, you see that pyridine, again, I told you, electric dipole effect. See, and that affects the orthoproton. Similarly, it affects the chemical shift of the alpha carbon also due to the. So that's why whatever I have told for proton chemical shift are all applicable for carbon chemical shift. They follow very closely. Okay. Similarly, if you remember, the carbon here will be more downfield than this, because this is attached to getting the full effect of both the aromatic rings compared to this and this. Here you can see that this one is getting the effect of all three rings. Okay, so that is the way the chemical, like exactly like your proton chemical shifts. Okay, carbonyl carbons are very important, and they will see that they come in a very specific region, delta 165 to 220 ppm, and you will see that their intensities are very less, except the acetaldehyde or aldehyde. See, the intensity is less. The main reason is the longer T1. See, in case of carbonyl, C double bond O, C double bond O, there is no proton attached to this. Okay, so that's why the T1 is longer. So that's why over the time, if you do a repetitive scan, you will see the carbonyl signals are got saturated. Saturated means no, there is no net absorption. So that's why carbonyl signals are very weak. But in case of acetaldehyde, in case of aldehyde, you get a slightly better signal because you have a hydrogen there. Okay. And you can see very easily identify ketone and aldehydes. They prefer to come below 190 ppm. Okay, specifically ketones come above 200 ppm. Aldehyde comes around 190 to 200, and remaining carboxylic acid derivatives, they come between 160 to 185. Okay, and then depending on the metal, suppose if you considering the metal carbonyl, you get a value depending on the what type of metal. If the metal is electron rich or if the metal is electron poor, it depends on that, is a variable. You can see it can vary to a large extent. And this is the carbonyl carbon of the carbon monoxide and carbon dioxide. These have been recorded in the saturated solution of CdCl3. Okay. Like carbonyls, there is another class of carbons are called the triple bonded carbons, and like proton NMR, carbon NMR also, they come quite uphill 70 to 90 ppm. Okay, in case of another triple bonded system is the nitrile group, but nitrile groups come quite downfield because the nitrogen is more electronegative, so it comes around 115 to 120 ppm. Okay, but the signal intensities are very weak because of there is no NOE. But in case of acetylene, you will see the internal carbon comes slightly downfield but with less intensity, because in the terminal acetylene, you get the NOE due to this proton, but internal, this you don't get this NOE, you get here no NOE. Okay, no NOE. We'll explain this thing, what is NOE, later on. Okay, timing, you understand that you can identify. Okay, so that's why you see around the internal carbon will come around 80 to 90 ppm. Okay, these come around 70 to 80 ppm, the terminal one. Okay, so so there is also the carbon chemical shifts like proton NMR, they depends on the steric effect. Okay, so if the molecule is sterically congested, you will see the carbon chemical shift goes to a higher value. For example, if you have let us say this is a molecule where the stereochemistry is such that the hydroxyl has to be axial. Okay, in that case, you will see the carbon chemical shift is uphill shifted. Okay, both the carbon and these carbons also, because the hydrogens are here are actually interacting. Okay, so you can see that this chemical shift, but if you consider the equatorial one, you see now this has now moved to downfield. Similarly, these two carbons also move to downfield. Okay, so there is a downfield shift when it is there is a less steric effect. Okay. Another example is that this methyl is exo, so there is a steric interaction between this carbon and this carbon. Okay, now if you see that in the in the endo structure, now you see that this steric congestion has gone. So this carbon has now moved from 35 to 38, but now the chemical shift of this has decreased because of this steric interaction. There is a shielding. So this is the general chemicals, general 13C chemical shift of all type of carbons, which I have discussed, are actually summarized in this chart. It is self-explanatory. You can see it. If you have doubt, you can ask me later in the later class. Okay. Now this is a very important thing, that if you know the chemical shift of proton, you can tentatively tell what should be the chemical shift of the carbon in which this proton is attached, or vice versa. Okay, so this is again an empirical relation which have been the relation have been found by studying thousands of compounds. So if you know the chemical shift of carbon, okay, the proton chemical shift attached to that carbon will be 0.0479 delta C plus 0.472. You will get an approximate value. If you know the carbon 13 chemical shift, you will get the approximate value of what should be the chemical shift value of that proton attached to that carbon. Similarly, if you know the chemical shift of a proton, and then you can tell tentatively what should be the chemical shift of the carbon which it is attached to. So it is delta C is equal to 20.9, delta is minus 9.85. Okay, so these are thus empirical relation. There may be a wide difference also between the calculated and the experimental values, but in many cases it matches well. So for an unknown compound, one can start with this, and then finally, as you use different spectroscopic techniques, you will get a final solution. So here I have shown the chemical shift values of various 19 fluorine nuclei, and the chemical shift range of fluorine is very large. It is up to 1300 ppm. You can see that the variation, okay, from minus 78 in one compound it is minus 441.5 delta value, and if you see this it is 871, so almost 1400 ppm. So fluorine comes in a wide chemical shift. Proton the smallest, delta are mostly between 0 to 10 or minus 10 to minus 20, sorry, minus 10 to plus 20. Carbon comes between minus 50 to 250. Fluorine comes around minus 500 to plus 1000. Okay, see, even phosphorus is also around 900 to 1000 ppm. You can see it is coming from minus 300 to minus 600 ppm. And the type of functional groups and their chemical shifts you are already shown in this graph, and it is easily understood, self-explanatory. So you just go through this. Okay. Similarly for 14 nitrogen chemical shifts, that is also the nuclei resonate in a wide range of chemical shift from minus 100 to plus 800. Okay. And here I have shown beyond those, there are many more nuclei which are being used, commonly used in NMR spectroscopy, like aluminium. Okay, aluminium is 129, silicon is there, then rest of the things I have told, 11 boron is there, 15 nitrogen is there, oxygen 17 is there, tin is there, platinum. You see the platinum 14,000, the chemical shift range is 14,000. Okay, tin it is 3,000. Okay, 31 phosphorus, although here it is showing greater than 300, but normally it is from in the previous slide only I have shown, it is coming from minus 300 to plus 600. Okay, so similarly oxygen 17 is around 900. Okay, ppm. 15 nitrogen 1000 ppm. Okay, 11 boron 200 ppm. Okay, so anyway, we are not going to discuss all these nuclei in detail. Most important nuclei I have discussed are the proton and carbon, and I have shown you the chemical shift range for various functional groups for fluorine, phosphorus, and 14 nitrogen. Sometimes those things will be used while interpretation of your NMR spectra. So I'll stop here. If you have any doubt till today, so I am completing my chemical shift lectures. So if you have any doubt about all three lectures which I have told in the about chemical shift of various nuclei, okay, you can write me email or you can ask me in the next question, okay, or you can ask me now also. I am available.
And tell about this assignment.
And so whatever I have taught so far in this 6th class, I'll give you one assignment, multiple choice of questions. Okay, I'll give it maybe in this week, and I'll give you 1 week time, and you have to submit it because it carries some mark. So when those who will be appearing for exam, this mark will be added to the final marks. Okay, so I'll give maybe Thursday or Friday lecture. I will provide you the questions. Okay, it will be multiple choice questions. Okay.
The question.
Sir, what decides the chemical shift range? Okay. इसको कैसे जाए फिर एक ब्लैंक जा सकता है क्या? See, the chemical. See, what we have seen, the chemical shift is solely decided. The what chemical shift? Actually, लिख के चलो. So chemical shift is directly proportional to the electron density. Okay, electron density on that nuclei and plus various other effects, specifically the magnetic, delta magnetic, okay, and delta electrostatic. Okay, so these three are the major thing. Okay, now if you consider to the, let us say, for proton, okay, so proton, these effects are comparatively small. Okay, so the change in the nucleus, whatever this B effective is equal to B0 into 1 minus sigma. Okay, so this sigma value, this is nothing but the sigma value. Okay, now this sigma value for proton is not that large. Okay, but for other nuclei, that value is quite large. Okay, so when that value is quite large, you get the B effective actually experienced by the nuclei is quite different between the two such. Let us say in case of hydrogen, what we have seen that mostly they come around 0 to 10 ppm. Okay, because of the, so you can find out what is the change in the what is the B effective for this, B effective for this. Okay, but if you go for, let us say, fluorine, so that is coming from minus 300 to, let us say, 1000. So this is your, you can find out what will be the B effective here, what will be the B effective here, and you will see there is a lot of difference. Okay, so the skinning constant, what we are telling, are very much depends on which nuclei you are studying. See, you must remember the proton is only having only 1s electron. Okay, but when you go to the other nuclei, they have the electrons in their p orbital, sometimes they have in the d orbital. So all those things makes a lot of difference in the B effective. Okay, that's why the chemical shifts are quite large. Clear?
Any other question?
Any other question? So, okay, you please go through all 3 lectures, or rather I will say all 6 lectures. If you have any doubt, okay, we can discuss in the next class. Okay, or you can send email to me. Attendance will be lower. Pardon? So next class I will start the spin coupling. Okay.
Next class is day after.
Thursday at 4 o'clock. Your next class is on Thursday, this Thursday at 4 o'clock. Okay.